Okay, today is conditional probability. Condition. If I said, I will let you learn today on one condition, that you stop talking so much. Okay, so if I gave a condition, it means we can do this, but there's this one thing you have to do. Conditional probability is like that. So if we looked at this, this is one of those charts from yesterday, okay, the tree diagram. And I said, given there were three different choices here. The first choice was, do you want to get a dog or a cat? Okay, that column is a choice. And then next, there's another dog or cat choice. That's like the second pet you're bringing home. And this is like the third choice. Now, it could be one family picking three different animals to bring home, or it could be three separate people choosing an animal. But they are done in order. It can't be all at the same time, because you got to know which way to go down the chart. So family one picks first, and they pick either a dog or a cat. And it looks like more dogs are chosen than cats. Does that seem likely in the real world? Yeah, I think that's probably true. All right. So if I said, why are we doing conditional today? Conditional means I'm putting conditions on it. Like, given that they had to pick at least one dog, then instantly it's out of something different. It isn't out of 100% anymore. Remember how these all add up? This number here, and this number, and this number, and this number, and this number, and that, and that, and that are all supposed to add up to 100%. One of them would get thrown out. Which one? Cat. This one's out. And now it's not out of one anymore. So if you said, I want the probability of this one, given that one condition, then I would find this one, but then I would take whatever this comes out to be. In fact, let's do it. Grab a calculator. If you haven't already got one, get one out. I'll pause for a second while you do that. So would you multiply out 0.57, 0.43, and 0.57? Here's why I'm having you multiply those out. Because, I'm going to choose a highlighter here. I'm saying, what's the probability of that one? I just kind of picked a random one. If everything was possible, then I just multiply them together, and that would be my answer. Just that. So what is 0.57 times 0.43 times 0.57? 0.131? 139? All right. Okay. So it's about 14%. Would you agree with that? Okay. So then if all things were possible, there's a 14%. It's going to be two dogs and a cat. And specifically dog, then cat, then dog. Okay? Because do you get two dogs and a cat could also be this way? That's also two dogs and a cat. Guess what you get when you multiply all those out? The same thing, 0.139. So two dogs and a cat, it depends on the order which one you're saying. So if you say, we've got to have one dog out of these, then we've thrown out this one. And then, if I wanted this highlighted one here, this row, what's the probability of dog, then cat, then dog? Then it's not 0.139 anymore, because it's not out of one anymore like it was in the first place. What's it out of? Well, it's out of everything else added up. This and this and this and this and this and this and this. That's what it's out of. So there's the smart way and the dumb way to do that. Think about this for a second. The dumb way is to add them all up, have to compute every single one of them. Take forever. What's the smart way? Subtract this one, because they would have added up to 1, except we can't do that last one, right? So they're going to add up to 1, so I say 1 minus whatever this one is. Because it's not 1 anymore, we got to take away this one that's not possible. So we got to do that. Would you please take 0.43 to the third if you're really smart? Because 0.43 times 0.43 times 0.43 is 0.43 to the third, right? Okay, and what is that? Point what? Oh, don't subtract the 1 yet. So we're 1 minus 0.095. Okay, so then there's your final answer for what's the probability of dog, cat, dog, given this condition. that we have to have one dog, that throws out the all cat situation. That is as hard as they get today. I wanted to start with the hardest one. Okay, so then let's do it just an easy one. What's the probability of dog, dog, dog? I didn't give you any conditions. No conditional. Just what's the probability of dog, dog, dog? So did you do just 0.57 to the third? And what'd you get? 0.185. So that's about a 19% chance that that would happen. Think about this. Technically, didn't I do 185 divided by 1? But dividing by 1 doesn't really do anything, right? Why do I say that? Because you're really dividing by all the things that are possible, and all of the things were possible, and everything added up would have added up to 1. It's only if I put conditions on it. Like, I'll give you a condition. Imagine for a moment, in this next slide, okay, that exactly 2 of the families choose dogs. So, again, there has to be 2 dogs. Notice I didn't say there even could be 3 dogs. There has to be 2 dogs. Find the probability of that. Did I ever say put conditions like given that I know blah, blah, blah? Nope. I just said what's the probability that exactly 2 kids choose dogs. So you really just have to figure out what routes work. Tell me why I'm wrong if I pick that one. It's more than 2 dogs. It's supposed to be exactly 2. How about that route? Could that work? Yep. So you have to figure out that answer. And there's more. There's quite a few more. Yep. Once you find them all, then this, or I'll show you another one. Let me use a different color highlighter this time. I'll use green. Dog, cat. Dog is a different one that has 2 dogs in it. That, or some other things. When I say or, you're adding them on top of a big fraction. All over what's possible. And in this case, since there was no restrictions, no conditions, everything was possible, which adds up to 1. So it's technically just dividing by 1 this time. They just said the probability that 2 kids chose dogs. I never said, given that 2 kids chose dogs, now here's a question about that. All I said was, what's the probability of 2 kids picking dogs? Exactly 2. And that kind of implies that 1 kid picked a cat, right? If 2 picked a dog, one of them must have picked a cat. All right. 0.57, 0.57, 0.43, that top number there. Miss A.S., what did you get for that? This one right here. 139. Okay. How about the next one? Oh, why? Same exact numbers, just in a different order, right? And there's one more. Okay, let me find a different color if I have another highlighter. I do. I use that one, and it's cat, dog, dog. And it's still 2 dogs and a cat, so it's still going to be the same thing, 0.139. So it's 0.139 plus 0.139 plus 0.139. Notice, these are ors. Get what I'm saying? This or this or this. And you add up all the ors, divided by all the things that were possible, which, since they were all possible, you can do it the dumb way and actually add all these up, or you can just know that they add up to 1. There you go. So when you actually add those all up, you get what is that, 0.5 something? 419? Okay. So what is the actual probability then that 2 kids will choose dogs? Say it like a normal person would say it. About 42% chance. Because it said exactly 2 kids chose dogs, as in not 3 is what they're trying to say. All right. This one. What's the probability that the kids will choose at most one cat? At most one cat. You got 3 kids picking animals here. Probability the kids will choose at most one cat. You obviously got to get, maybe it's multiple things, but you got to get some routes that you think work. Let's say you think that works. Then that's one of your answers. And you'll take your answers, and if it's this or this or this or this, you're just going to add them all up and figure out if there was any conditions. Is it? At most one cat means they'll have one cat and 2 dogs, or one other thing, 3 dogs. Because wouldn't that still fit the category of at most one cat? Because then they're kind of saying it was actually 0 cats. So dog, dog, dog gets added to the other ones. So we had 139, 139, 139, and the last one is dog, 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 which we have to add in now. 185, and so that makes a grand total of over 50% now. What actually does it come out to? Can anybody verify that? 0.06? That doesn't make sense. 6042 or something like that? Okay. So about a 60% chance that that would happen. Yes? Good question. Is this dependent or independent? When the kid goes in and picks an animal out of the shelter, does the probabilities change for the other kids? I know it's kind of a good question, because if there's less dogs actually in the real world, I'd say the probability is lower that the next kid's going to pick a dog, because one just got picked, there's less dogs to pick from, and so maybe in the real world it might be dependent. But this problem is meant to be independent, because the probability is not changing of a dog. See how this and this and this are the same? That's kind of a hint that the probability is staying the same, and so what happens here doesn't depend on what happened here. Get what I'm saying? So if you go in and you pick a cat, does that change his mind about what he's going to pick? No. Although in the real world it might have, because but the numbers aren't changing. So go ahead. Yes. If it were dependent, okay. Then no, that would be if you had a deck of cards, for instance, and you take a card out of the deck, once you pick it, you take it out. That changes the probabilities for everyone else. Okay. So in a way, you could argue that this dog problem should have been dependent, because now there's less dogs to pick from. But they're saying that it's in the original problem that we never even really read through. They're saying that people are just more likely to pick dogs. And if they just take data over time, if the average person comes in, there's a 57% chance they're going to take a dog home versus a cat. And so that's just a general percentage, and notice it's not changing at all. These 43s are staying consistent, and the 57s are staying consistent. That's a way you can tell this one's independent. If it was dependent on the card thing, for example, if you had, you have 52 cards that you could pick from, and let's say that the probability you're going to get the ace of diamonds, and then there's everything else. Do you get the ace of diamonds? There's only a what chance? 1 out of all the aces, no, all the cards, which is 52. And then everything else is a probability of 51 out of 52. Think about it. These have to add together to make 1. Okay. Then what makes it dependent would be, now if you got an ace, now what's your probability? Doesn't it change? If you already got the ace of diamonds, now what's the chance on the second draw? If you already got the ace of diamonds, there's a 0 out of 51 chance of getting the ace of diamonds, because you already got it. Okay? And there's a, think about it, what chance of getting something else? 51 out of 51. Do you get how these numbers changed when you got here, it's because it depends on what you picked the first time. That would make it dependent. All right, back to this kind of a problem. Get to this one. Given, ooh, that's a condition. It's kind of like given that you're willing to wash the car, then I'll let you use it to take your date to the prom or whatever. Given this condition, well, here's the given. Given that the first kid chooses a cat, that changes what it's out of now. It's not out of 1 anymore. Now you have to divide by something. So whatever you think is on the top added together, now you better divide it by something different than 1. It is not 1 on the bottom. I'd like you to see if you can figure this one out without me. Pause for a sec. Okay, here's how I would have done this one. Given that the first kid chooses a cat, changes everything. If the first kid chooses a cat, this whole part of the chart is impossible. So if you picked any of those numbers, you did it wrong. Do you get how scribbling that out narrows it down a lot? Why do I do that? Because this would be if they picked a dog first. It said that's not true. It said that the first person chooses a cat. You have to be choosing from only these numbers. How many of you actually did that? Okay, good. That's a good start. Now, let's see if you actually get it right. Now that that's the case, do you get, I really need to figure out what all of these add up to? Now, there's a slow way and a fast way again. The slow way is to calculate each one of them and add them all up. But who sees a faster way? Yes, sir? They have to all add up to 0.43 because of that. Now, if you didn't notice that, that's okay. And if you added them up and it didn't actually add up to 0.43, it's probably because of rounding. It was really close to 0.43. It's probably because of that. But they should have added up to 0.43. Now, which are the ones that win? All the kids choosing cats. That's this one, 4-3, 4-3, and 4-3. And there is only one. I don't have to add up a whole bunch of choices. There's only one thing, that one right there. And that goes on top. What was that? What is 0.43 times 0.43 times 0.43? What do I put here? Thank you. And then when you actually divide these two, final answer, 0.18. About it, around it, I suppose, 18%. How many of you had that? Okay, good. If you didn't, yes, you could ask.
Like, given that the first kid chooses the cats, and then I crossed out the other stuff.
Okay, that's good.
Why would that change the other kids?
So you're thinking that this answer should have just been 0.079. Is that what you're saying?
Yeah.
Okay. You felt like the answer should just be 0.079. Here's the thing. If we know ahead of time that the first person chooses a cat, don't you think it's more likely then to happen? Because this was if anything could happen. It was only 8% chance, but that's if anything could happen. Now I already know that the first kid's picking a cat. It increases that probability. And this is the way of telling how much it increased it. You divide by what's possible. Instead of dividing by 1, you divide by all of these added up. All of these that were possible here added up, and they add up to 0.43. All right, that's why it's a higher chance. See, you thought it was about 8%. In the real world, it's actually 18%. It's a higher likelihood because we already know the first thing was a cat. All right, let's move on. These are mind benders. This probability is the hardest probability in the school, honestly. So don't be surprised if this makes you really think twice or 3 times. Classic grumpy cat. It's a real cat.
My grandpa met grumpy cat.
Awesome. At a cat show or something?
Yeah. It was like Boy Fair in New York or something.
Incredibly famous cat.
Yeah.
I actually, for a while, I knew what the deal was. I think, isn't she just got like, I don't know, just kind of looks like that.
Yeah.
It's some kind of a condition or something, you know? I know it's not like a degenerative disease or anything, but it's just, yeah. That one eye being open not quite as much as the right ear being tilted just a little bit all adds to the effect. All right. Given at least one kid chooses a dog. Okay, I can't just go cross off a whole bunch of part of the table here all at once. It's not as simple as, oh, it's all gone now. But you can cross off some things because some things aren't possible anymore. At least one kid chooses a dog means that's a different way of saying something I said before. You just can't use all cats. This is the only one that's not possible. So again, you could do it the dumb way and figure out all of these and then add them all up and put it on the bottom. The smart way is to take 1 minus that one because they would have added up to 1, but now I'm taking away this last one. What is 434343 again? 079. So it's 1 minus 0.079 on the bottom. Then the question is, what's on the top? At least one. Uh-oh, wait a minute. I may have read this wrong. Given that at least one kid chooses a dog. Okay, wait a minute. That means it can't be all cats, that's for sure. Okay, I did that right. What's the probability at least one cat is chosen? Okay, I haven't done anything wrong yet. Okay, now I'm reading this part. At least one cat is chosen. So ask yourself, in this spot, was at least one cat chosen? No, it's not one of the ones we pick. In this, was at least one cat chosen? Yeah, and I think you're going to find that all the other spots have at least one cat chosen, haven't they? All right. No. The given was that at least one kid chooses a dog. This doesn't break that. Okay. Just stop. let her. I hear you. And I do get when somebody's trying to help a kid. I appreciate that, but at the same time, the kid asked me, "Give me a second and let me try to answer it for him." And if I'm too busy with somebody else, then I'll absolutely answer it for them. But, all right. I get paid the big bucks for answering those questions, so let me do it. All right. If I'm busy, though, then that's great. Okay, so hopefully you found this and this and this and this and this. Oh, crap, that's a whole bunch of things to find. Wouldn't there be a smarter way? Yeah. You could take 1 minus what? This one and 1 minus that one. 1 minus both of those would give me everything in between. Again, you want to do it the slow way? Find each one of them and add them all up. Want to do it the faster way? You take 1 minus this and that. So I'm going to say 1 minus 0.079 minus another, what was the top one? The dog one. 185. And there's my answer. I know that was tricky, but it could have been, if you'd rather, I'll do it with a highlighter here. You could have added up this one and this one and this one and this one and that one and that one, and it would have come out to the same thing as that. Just trying to show you shortcuts. If you don't like the shortcuts, you want to do it the long way, as long as you understand what to do, it's okay. All right, the biggest, most important thing was the beginning there. That sentence I circled, given that at least one kid chooses a dog, right here. Do you get that left everything possible except this last one? That's really key, okay? And that's why we did this, because these would all add up to some big number, but it would be easier to find it by taking 1 minus that number. Question? Is that making sense? Okay, good. All right, next one. Oh, that's just saying the easier way, which I just told you, which was this is not possible, so you add up. You don't add up all of these. You go 1 minus that one. Okay, moving on. The chance of rain on Monday is 56%. Do you get that's the beginning of a tree? What were the two things that could happen on Monday? Rain, not. Okay, so what's the rain side? 0.56. Actually, I should move the rain over. Should move rain to over here to leave room for the probability, which goes right here. and not rain. Well, therefore, logically, if it's 56, it must be 44. Do I have that right? All right. The chance of rain on Tuesday, ooh, notice, these are separate events. That was Monday. This next one is Tuesday. Chance of rain on Tuesday is 17%, okay? So then, on Tuesday, 17% chance, 71, I get dyslexic for a moment there. 17% chance of rain, and not. And if it's a 17 here, then you logically know that one has to be 83. Okay, good. And then not rain, same probabilities though. This is the same thing. This is about Tuesday. It's not about what you picked before. You think Monday or Tuesday cares what happened on Monday? No, it doesn't. So then this one's 17 and 83. Excellent. Okay. And the last one is on Wednesday is 51. So here's Wednesday. And you got two branches, rain or not. And there's two more down here. It's huge. Yep, like Bernie would say, huge. Now it's just a little too messy. Okay. There we go. Now we made this huge chart. Huge chart. Then, probability that it rains exactly 2 days given, oh, there's conditions on it. It's like, okay, so this is conditional, which means there's conditions. Given it rains on Tuesday changes everything. If it rains on Tuesday, now scribble out the part of the chart that's not possible anymore. If it rains on Tuesday, you can't go down which paths? Can you see it? You can't go down any of these paths there, can you? Is there anything else that just got knocked out? Yeah, the bottom one where it says not. Here's another Tuesday not raining. Those are all out. Now, my new probability, don't forget when you do that, your answers still go on top, but you have a new number on the bottom. And the new number on the bottom is everything added up. This one I don't have a neato trick for you. You just have to figure out this answer and this answer and this answer and add them all up and put it on the bottom. Take a second and do this one. I know it's involved, but it's the last one I will do. I'll pause for a second when you try that. Okay, I wish I knew what number was on the top and what number was on the bottom, but you should have gotten 0.499. If you're only off a teeny bit, it's probably because of rounding. Raise your hand if you got the same thing. That's a bunch of you. And if you did, can you tell me what the top number was? If you got an answer that was really close to 0.499, what was your top number?
0.499. I think it's supposed to be.
Oh, it could be off by a decimal point. Is it 0.0499? Well, tell me what the top number is. If you think it's 0.0499, you're probably right. Okay, I'm going to pause for a second. We figure this out. Okay, the kids are just dismissing here, but this is how you do this one. You add up the circled ones and you put them on the bottom. And then the ones that would work here would have been this one had 2 days of rain, exactly 2 days of rain. And this one had exactly 2 days of rain. And so those two are the things that we want. They get added together on the top here. And when you divide those two, that's when you get this 0.499 answer. That's all I got for you for today.